This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
So welcome everybody to the seminar Cog Neuro. Today we'll be talking about OPMs. It's really exciting to have Matt Brookes all the way from the University of Nottingham and also his colleagues over there, David and Holly, who have been helping out in the lab as we set up this week. So it's really MEG crunch week for us, so it's exciting. I would also like to acknowledge that we gather on the lands of the Wurundjeri people. They've always been making discoveries and sharing knowledge and teaching in these lands much before the buildings of the University of Melbourne were built. So we continue that today. So I'm very excited to introduce Matt Brookes. He is an absolute pioneer in OPMs and MEG. He is a professor of physics at the Sir Peter Mansfield Imaging Centre at the University of Nottingham in the UK. His work centres on the development and application of multi-modal brain imaging, particularly MEG, where and over the last 20 years, his group has made significant contributions to inverse modelling, connectivity measurements, clinical applications, and development of MEG hardware using OPMs. And today he'll be talking about neurodevelopmental data as well, right? So that's pretty exciting for some of us in the room. He's been the recipient of many awards, including the Blavatnik, I can't say it properly, Laureate Award in Physical Sciences and Engineering in 2022, and an OBE for services to physics in 2024, which is really amazing. So thanks, Matt. Take it away.
Brilliant, thank you. Thank you for the, oh, is it recording? Do you want to press go
yes.
on some?
Yes.
Awesome.
Everything's been recorded.
Excellent.
Okay, cool. Yeah.
So yeah, thank you, Martha. Thanks for the invitation to speak. I think this is the room with the best possible view that I've ever given a talk in. So if I sort of get distracted, maybe bring the blinds. So in this talk, what I wanted to do is just share some of the experiences that we've had over the last 10 or so years in Nottingham working with OPMs. Obviously, you've got an OPM system that's being installed literally now. So welcome to the club. And yeah, we'll talk a little bit about what OPMs are, why certainly I'm excited by them, and perhaps say a little bit about what we've been using them for. So is everybody familiar with what MEG is? Yeah, so I don't need to say all of this stuff. Right, but basically what we're trying to do, we have some currents going through neurons in the brain. They make magnetic fields. Those magnetic fields pass through the head, and we stick a load of sensors around the head. So that's a conventional MEG system in Nottingham. So lots of sensors around the head, and we're measuring these magnetic fields. Magnetic fields themselves aren't that much use. If we take our magnetic fields, apply a load of mathematical rubbish, which I'm not going to talk about, we end up with images like this. So we can work out where in the brain currents are changing, and in that way we can infer electrophysiology. I could talk forever about all the reasons that MEG is great. I'm not going to, but I could. Example use case, things like basic science, understanding what brain activity is and how the brain works. MEG provides a very complementary view of electrical activity, of brain activity, compared to other techniques like functional MRI. So functional MRI, most of you will know, measures blood flow, hemodynamics, and we're measuring the electrophysiological counterpart of that. So I mean, most MEG people would say we're perhaps a little bit closer to brain activity than fMRI. We've got better spatial resolution than EEG. I'll say a little bit more about that later. Biggest clinical use case of MEG is epilepsy, so this is epileptic data. So these spikes in red, They're epileptic spikes. They're things that shouldn't be there in the electrophysiological data. And we can work out where those spikes are coming from. That provides useful information for neurosurgeons. Lots of other areas of research, dementia, mental health disorders, childhood disorders, and also new cool application areas like brain-computer interfacing. So there's lots of things that we can do with a MEG scanner. Lots of reasons why we should be excited by this technology. But actually what I want to talk about is why it's annoying. Okay? So what are the limitations? So this is our conventional MEG system again. And the first thing to say is that to make it work, a conventional MEG system uses sensors called superconducting quantum interference devices, or SQUIDs. And the bad thing about SQUIDs is they have to be kept very cold to work. So they're kept at minus 269 degrees. That means that you can't put them close to the head, because if you do, you get chilly. So they need to be a long way away from the head. So they're about 2 centimeters from the head. And that means, and as you move away from the head, the signal from the brain, the magnetic field that we're interested in, decays with the square of distance. So if we double that distance, we quarter the signal, and that's a bad thing. So even at the best that we can do, so here's somebody whose head fits the scanner pretty well, but the sensors are already a long way away from her head, meaning we've got low signal to noise ratio. That's an adult. If you imagine putting a child in there, obviously their head is smaller, so the problem becomes even worse. So neurodevelopment is actually pretty challenging with these machines. I don't know if any of you've got kids. I do. I can't keep my kids in the same room as me, let alone in a scanner, and so kids find it very hard to stay still. If you get out of the system, or if you move around, it degrades the data quality. It's not just kids, you know, there are lots of movement disorders. Patients that we've scanned, in particular patients, we did a lot of work with schizophrenia, really struggle to stay still, so you end up throwing half the data away. And probably the biggest thing, these things are very expensive, not only to buy, they'll cost about $2.5 million US dollars to buy, but they're also expensive to run. They drink liquid helium, you need helium reliquefiers. Obviously that's bad for the environment. So I think these sort of capture some of the reasons that technology isn't great. So some years ago, working with Gareth Barnes, who I know you know very well, in London, and I think probably Gareth and I were in the pub, which is where all good ideas start. And we said, well, why can't we turn this into something that looks like this, something that looks more like a sort of EEG type system. And it wasn't quite, you know, as stupid as it sounded, because we've been following for a long time the vast amount of work that had been done on the development of what were then called atomic magnetometers, now called optically pumped magnetometers. But the idea, the promise of using these newly emerging sensors was becoming more and more of a reality. And so we started to think about it really serious. And so that's what happened. These were the original OPMs that we used. This was the first generation Q-spin OPM. It's actually quite big. The footprint, this is the part that sits on your head, so it comes on your head like this. That footprint, it was about 2 centimeters by a centimeter, but it was about 10 or 11 centimeters long. So these things stuck out of your head, looked a bit like a hedgehog or something. And then later the sensors got smaller. So these really are sort of Lego brick sized sensors. And the OPMs that was going in your lab, I think pretty similar size. This is a third generation Q-spin. This is roughly how they work. So inside each OPM is a photodetector, a glass cell with some atoms in it, and a laser. These are usually rubidium atoms, not always. You can make these things with other types of atom, but your sensors and our sensors are rubidium. And so the sort of hand wavy view of what's going on is each of those atoms has its own little magnetic moment. And what you do is you switch on the laser, and the laser acts to align all of those magnetic moments, so they all point along the same direction. So for anybody who's done MRI, it's a little bit like what the magnetic field does in MRI. In MRI, you turn the protons around to point along the direction of the field, and that's exactly what we're doing here. We're just doing it with a laser. Is anybody here a physicist? Just for the once upon a time physicist, what you're actually doing is you're pumping on the D1 line of the energy level structure of the rubidium atom. You're pumping with circularly polarized light. So as well as changing energy states, you're also giving these atoms angular momentum. It's the angular momentum that allows them to click round and all point in the same direction. So every time an atom absorbs a photon, it's these transitions that you're driving. So this comes from Holly's paper. So Holly wrote a review paper on that. So if anybody's interested in the proper physics of how these things work, but it is, I promise, it is really interesting. Physics is great. So then what happens? So we have all these things. Just go back. We have all these things pointing in the same direction. But this is what happens at zero magnetic field. So we're assuming that the magnetic field around this cell is zero, and that's why these things are sometimes called zero field magnetometers, because they operate at zero field. But what happens when we bring a source of magnetic field, like the brain? So we know the brain generates magnetic field. Bring the brain close. Now this gas of atoms that's in our cell is now magnetic because they're all pointing in the same direction. So if a magnetic field passes through it, they're going to wobble. So they wobble like that. And what that means is, so when they're all aligned, because they're all aligned, so we use the light, the laser light, to align them. But once they're all aligned, they can't absorb any more laser light. So the laser passes straight through the cell. But when they're not aligned, now all of a sudden, they can start to absorb laser light again. And when they start to absorb laser light, this part over here, there's less light getting through the cell. Does that make sense? Yeah? So in this case, when they're all aligned, all of the light goes through the cell because they can't absorb any more. And this here, because of the magnetic field, they can start to absorb the light. Again, for the once upon a time physicist, what we're actually doing is, so that bulk magnetization, that swinging around of the atomic magnetic moment, follows something called the Bloch equations. So if we take that away, that term there, that's the basic Bloch equation. If you put that term in, what that's doing is a modulation field. It's kind of complicated, but you can solve the Bloch equations to get this. So this here is effectively a graph of the signal that you get out of an OPM. So that's what the photodiode reads against magnetic field. And obviously it's a funny looking function, but that little bit in the middle, again around zero, looks like that. And that little bit in the middle is linear. So we have a machine, if you like, a sensor, where if magnetic field changes in that range there, then the voltage output will change. So that's how it works. This has been the sort of Nottingham-based journey for OPM MEG since around about 2014. So when we first started, so this here in the scanner is Elena Boto, who some of you may have met. So she joined us in 2014, so 10 years ago. God, I'm getting old. And we started to think about this. We started with simulations. Then we got the first OPM from QSpin. and we only had one. This is Gareth. We scanned Gareth up in Nottingham. Gareth came up. We only had one machine, one sensor, and we obviously wanted to measure the magnetic field at lots of different places on the head. So he did the same experiment 13 times. It sort of looks okay, but what you can't see here, this is a 3D printed mass that fits. It was based on his MRI scan, so it fits him perfectly, and so he can't move in the mass. And this was bolted to a bed, which was bolted to the floor. And we did the experiment 13 times, so he's there all day. And I just remember him sipping coffee out of a straw while he was lying there. But it obviously wasn't very practical to bolt people down. So by 2018, we'd worked out a way, which I'll talk about later, of allowing the system to move, so you can move your head, and the sensors move with your head while you're being scanned. The sensors got smaller, so these were the first generation sensors. These are the third generation sensors. By 2020, we had a 50-channel system. 2022, we had a 192 channel system. 2023, we had a system for children, and actually Holly's just built. We need an extra box now. Holly's just built a 384 channel system, of which how many work?
352.
So we've got a 352 plus or minus a few channel system at the minute. So yeah, we need extra. Yeah. So yeah, that's what we've been playing around with. A few just examples of early studies. So we knew we had a system that you could move your head in, and we wanted a good paradigm to sort of say, well, what can you do while you're moving your head? And so we dispatched Gareth into town, and he came back with the world's worst ping pong set. So this was the experiment where you sort of play a little ball game, and this was measuring beta oscillations. You can see a beta desynchronization during the movement, localized quite nicely to the areas that control the sort of wrist and arm. So that was the first. They were the first experiments that we tried to do. The point being not that we're particularly interested in what your brain does when you're playing ping pong, but if you can measure somebody's brain while their head's bouncing around playing ping pong, maybe you could measure a child who's having an epileptic fit or something. Over the years, we did lots of other cool things: virtual reality, cortical tracking of speech. We did some hyper scanning. So scanning, this is me and Elena playing ping pong against each other. There's a ping pong theme in the lab. We had two bats, so we thought we better use them. So simultaneous measurements, again, just to prove that it was possible. And I think some people are now quite interested in this idea of hyper scanning. This is a great paper by Sophie, who's currently in the lab here. She worked on designing an array to specifically measure the cerebellum. So most MEG systems are actually quite bad at looking at the cerebellum. So obviously, because of the flexibility, you can put OPMs anywhere. You can design an array specifically to put it right down near the neck and to look at cerebellar signals. So that's what Sophie did a few years ago in 2019. We've got a driving simulator. We've tried to scan people while they're learning to play a violin, which sounds absolutely awful in the lab. We've done some BCI stuff. So I thought I'd talk a little bit about what our system looks like now, the sort of advantages and disadvantages, and the way we've tried to design it. And it's probably worth saying it's not dissimilar to the one that you're going to be operating later today. So what is different about our system is we use triaxial sensors, whereas your sensors measure MEG in two axes. It measures magnetic field along two directions. We use sensors that measure magnetic field along three directions. Now, so I showed you a diagram before. I said we actually measure we measure magnetic fields using the atoms and using the lasers. But an OPM is most sensitive to magnetic fields that are either that are perpendicular to the laser, so either going up here or across here for this laser. They're not completely insensitive, but they are less sensitive to a magnetic field that's going along the direction of the laser. So if you want to be really sensitive, which we need to be to get MEG signals, then we can only measure perpendicular to the laser. But if you've got two laser beams, then you can measure these two orientations with that one, and those two orientations with the other one, and then you can put everything together. So you have two perpendicular laser beams, and then you can measure magnetic fields in all three orientations. We weren't entirely convinced that this would work for a start, because the way you get these two laser beams is to take one laser beam and split it into two. And that means that half of your photons in your laser beam goes one way and half of your photons go the other way. And that means that you get higher noise because you've only got half the laser beam effectively. So we thought, well, these things are going to be much higher noise. And they are higher noise. So they're higher noise than the original Q spins, they're higher noise probably than the field line sensors, but not that much. So they've got a noise floor of about 15 femtotesla per root hertz, compared to something like 7 to 10 if you're operating single axis or dual axis sensors. So they're higher noise, so lower sensitivity. So you think, well, why on earth would you do that? Why would you want to get rid of sensitivity? Surely we should just use the dual axis sensors. Well, first of all, they may be slightly higher noise, but we can still measure MEG signals with them, so they're absolutely fine. We can also see the direction of the fields. So these arrows here are just 4 triaxial sensors showing how the field loops around a current that's somewhere buried in the brain. But the real reason that we got quite excited by the triaxial sensors was this. So let's say we've got 2 magnetic fields. This one is a uniform magnetic field that's going just across the helmet. Now, the brain can't generate a field like that. That field could only be generated by something a long way away, like a light bulb or something. So interference, the stuff in MEG that plagues the MEG signal that we hate, right? And then if so, okay, well, let's pretend that we do what a conventional MEG system does, and we're only going to measure fields that are radial to the head. So that's what a conventional MEG system is. And here, so what are we going to measure? Well, at this sensor, we'll measure a field that's looks like it's sort of coming inwards. And at this sensor, we'll measure a field that's going outwards. And at this sensor, we'll measure absolutely nothing. So that's what a conventional MEG system would measure. So field going in, field going out, nothing. Here's another field. That's a field that's going round like this. Now that could be generated by the brain. Okay. Again, if we only measure radially, so if we do what a conventional MEG system does, we measure a field coming in, a field going out, and nothing. So here we've got 2 completely different fields, but actually when we measure it, they look very similar. And that's a bad thing because we can't tell them apart. But if we add triaxial sensitivity, now all of a sudden we can measure something at this sensor here. And in this case, it's a field going that way, and in this case, it's a field going that way. So the 2 fields are suddenly easy to differentiate because we've got sensitivity to a field that's in this plane that we didn't have before. So that's just a cartoon. What actually happens in real life? Well, if we look at the similarity between interference and brain signals, then we measure it and it looks like this for a conventional MEG system, and it's down here for a triaxial system. Now I'm talking about triaxial systems. It also works for dual axis. Yeah.
What do you call conventional system? Because
SQUID system.
So SQUID system as planar gradiometers, magnetometers.
Yeah.
What kind of? Because I think the problem could be solved partially by planar gradiometers too, right? With the field being, the flat field passing through the head.
So the the planar radiometer will in part solve that problem, but they are still quite susceptible to interference. Here,
These numbers are for.
this was for a CTF system. These simulations were for a CTF system. So this is actually what happens in reality. So these are all OPM data now, but this was a radial measurement only, and this was a triaxial measurement. And you can see this line here, that's interference caused by an air conditioning system. We know, we turned that on in the lab. And if we use just radial reconstruction, you get this horrible line, and if you use triaxial, it goes away. So we really can get rid of external interference. And it's really important that we were able to do that with OPMs, because OPMs are magnetometers, they're not radiometers. Another way to think about it, those of you who've used MEG might be familiar with something called max filter or signal space separation. So this is what the MEGing system does, formerly the Elector system. So it's a brilliant paper by Samu Taulu from 2005. And what Samu did was invented this idea that we've got signals coming from inside the brain, inside the green circle. We've got signals coming from outside the brain, so outside the red circle. And you can decompose the signals that we measure at the sensors into a set of signals that come from the brain and a set of signals that come from outside the brain. And then in principle, if those two sets of signals were completely orthogonal, you could just delete one. And this is how the Elector system actually works. This is why they get really nice data. But it's reliant on you being able to differentiate those two basis sets. And you can always mathematically identify an angle between those two basis sets. So it's conceptually quite challenging to think about, but the only thing you need to realize is you want that angle to be 90 degrees. If the angle is 90 degrees, you can completely get rid of one, okay? So you want it to be 90 degrees. In the MEGing system, it's actually around 13, 14 degrees, something like that, depending on how we do the reconstruction. For a dual axis system, which is this one that's going to be similar, when we did the simulations, it was about 40 degrees. So it's massively opening up that angle. For a complete triaxial system, it's around 60 degrees. So see, we want it to be 90. We're not there yet. But for this array, we're getting to about 60 degrees. And that means that we're much better able to differentiate fields from the brain compared to fields from outside. Just another thing to look at, for those of you who are interested in neurodevelopment, we're now getting sensors very, very close to the head. And as a sort of naive, slightly stupid physicist, the first thing I thought was, well, the child's head's just a smaller version of an adult's, right? And it's not, it turns out. So the brain is scarily close to the skin in the child. So in an adult, it's about 1.5 centimeters. In a child, it can be about 5 millimeters. So the brain is very, very close to the sensors. And obviously, you've only got a certain number of sensors. So if you start putting the sensors across the head, what you can do is actually spatially alias the brain. So you get a sensitivity profile. So this is a 2-year-old. You can see you get these hot spots. So you become really sensitive to a relatively small number of bits of brain. And this actually played out when we tried to do the first experiments in children. What we found was some days it was amazing, and then some days it was rubbish. And we couldn't work out why for a long time. And it turned out that what we were doing was just by putting the helmet on a slightly different place, you would move that hotspot around. And sometimes you'd get it right on we look at the sensory cortex. So you'd right on the sensory cortex. And then other days, nothing, just didn't work. Whereas if you use triaxial sensitivity, actually you can see it really makes that coverage nice and uniform. So as soon as we started to use triaxial sensors, we were able to see signals in children all the time. It came a lot easier. Okay, how do you have time? So everybody always asks the question, can OPMs do the same thing that SQUIDs can do? And this is recent work by Zoe Tanner, who's in Nottingham, and it also works part-time, 50% of her time for Circa. So she wanted to compare the two systems, the SQUID system and the OPM system, and we thought one fun way to do it would be through neural fingerprinting. Has anybody heard of neural fingerprinting? People? So this is the idea that if I scanned all of you and then I scanned all of you again tomorrow, I could just use the data and see who was who. Okay? Your brain activity is a unique signature of you. Okay? But actually, let's say we put, I don't know, the two of us in a scanner, and we had identical brain activity, right? But I'm told I've got a big head, right? So my head is bigger than your head, but our brain activity is identical. We would still be able to tell each other apart because my brain is closer to the sensors than yours. Okay? So is this neural fingerprinting just an artifact of some people have a big head, some people have more? Okay? So what we thought was actually, if we compare this to this and try and do neural fingerprinting, first of all, if we can tell who's who across the two systems, so if I can identify you based using OPMs based on your SQUID recording, that's telling us, hey, these two machines are giving us the same information about a group of people. But it also helps to say, actually, if we can do it with this compared to this, it's more likely that there's a neural component, that it really is picking up on the brain signals and not just the fact that somebody's head is bigger or smaller. So that's what we tried to do. So here's just an example. These were two subjects, subject 5 and subject 14. This is the OPM MEG data. It was a sensory task, so you got 5, 1, 2, 3, 4, 5 sensory stimuli. This is the beta desync and rebound following each of those 5 stimuli. So one subject, another subject. And the first thing you see, okay, the two subjects are different. This one's there's more noise. Okay, this one's got a slightly bigger desync. But you'd look at those two things and say, well, it's kind of the same thing, right? And so, well, maybe the scanner was having a bad day. That's the OPM data. When you look at the SQUID data, again, recorded completely independently, again, lower signal to noise, deeper blue bits. The beta rebound seem to get bigger as the trial goes on. Whereas in this subject, they don't. So you can already see the sort of basis for this fingerprinting. These two signatures are different, but they're consistently different across the two people. And then if we did this, so we did this with 15 people, that's really hard to see on there, or maybe it's just my color blindness. But basically what you want is, if you can identify people, you want a dot along the leading diagonal of that matrix. And so we were able to identify 15 out of 15 people using their SQUID MEG data compared to their OPM. So these two machines really are collecting the same information about people. So, okay. So we can do the same thing with OPMs as we can do with SQUIDs, and that's been the question. Can OPMs do what SQUIDs can do? But I think it's the wrong question. I don't think we should be saying, can OPMs do what SQUIDs can do? I think we should be saying, can OPMs do what SQUIDs can't? Can they take things further? Can we do more with them? Rather than just saying, well, they're a bit cheap. And so the first thing you think about is, well, if you go back to the original papers, on theoretical papers on OPMs, because OPMs can get closer to the head, they should be more sensitive. Okay? And so we should be able to measure brain activity with lots more sensitivity than we can with the SQUID system. But does it work? Well, no. Partly because OPMs have a higher noise floor. So the noise floor of most OPMs is around 10 per root hertz to 20. Depending on exactly what type of OPM you have. Whereas the SQUID is more like 5. Okay, so we brought up that noise floor. So, but we're compensating, we're getting closer to the head, but actually the two things kind of cancel each other out. And then he said, well, the other problem is most OPM systems have fewer measurement channels. So you can't, a SQUID system will have 300 or so channels. An OPM system might have anywhere between 50 and a couple of hundred. So it's like comparing apples and oranges. You've got so many more channels that by the time you do source reconstruction. So actually, this was an image showing how much better OPM should be, but we're not there yet. And also OPMs are magnetometers, whereas, as you said, you've got radiometers in most SQUID systems.
I'm not sure how many people here know what the difference between the
Okay.
radiometers and...
Sorry.
Do you want to say a few
Yeah.
words about that?
So you want to be as sensitive as you possibly can be to the brain. And the magnetic field from the brain, as I've said, will fall off very quickly with distance. So one way to make yourself more sensitive to the brain is, rather than measuring the magnetic field at the head, you measure the magnetic field gradient. The easiest way to think about it is going away from the head. So if I can measure a big magnetic field gradient between here and here, then I can be more sure that that's a signal that's coming from my brain compared to something over there, which won't change very much over distance. So that's what a gradiometer does. Whereas a magnetometer just measures magnetic field. Okay. So gradiometers are advantageous. But you can make OPM gradiometers, but they're much more complicated and more expensive. So how do we actually realize this theoretical difference in sensitivity? How do we make OPMs more sensitive than SQUIDs? Well, the answer is really simple. Rather than putting all your OPMs equidistantly, what you can do is you can put them wherever you want. So you take all your OPMs and you just stick them on one bit of the head. Ideally, you'd like a 1,000-channel system, right, with OPMs everywhere. Because obviously, by sticking them all on one area of the head, you gain sensitivity, but you lose whole head coverage. So ideally, you want 1,000 sensors or whatever, but you can't do that. So we're going to take all of our OPMs and stick them in one place. So this is an example of a high density helmet. So you can see there's lots and lots of slots for the OPMs to sit in. This is a visual gamma response. I don't know if people have seen these before, but you sort of stare at these funny patterns and it makes really, really nice gamma oscillations, high frequency oscillations in the brain. This is what we got with a sparse array. So this is a sort of standard array where all the sensors are equidistant across the head. Yep, we get a visual blob, and yes, we get a nice little bit of gamma. But when we take all of our sensors and put them on the back of the head, so we have a really nice high density array, we get a much bigger signal. And we were able to make these measurements simultaneously. So the sparse and the dense array were operating at the same time in the same subject. So it's the same brain processes. We're just much better able to sample it. But it's kind of obvious, isn't it, right? You just measure more stuff by putting all the sensors in the same place. This was another experiment that we did watching natural scenes. So watching video clips of people walking around a city. Get this really lovely broadband gamma effect now that starts about 30 hertz and goes all the way up to about 140, 150 hertz. So it's a really nice experiment. Again, localizes the visual cortex as you would imagine. We recorded this with a high density array. This is work by Ryan and Holly. Holly's in the corner, but she's not on the slide. Sorry, Holly, you're behind the thing.
She's also there. We can just
So we measured signal to noise as a function of basically channel density in a funny sort of way that I won't go into. But by basically having increased channel density, we can make our signal to noise go up and up and up. And this was the mean signal to noise of a load of measurements on the SQUIDs using the same paradigm. So actually, we can increase our signal to noise of an OPM array much beyond what a SQUID array can do, which is kind of nice. And because this is linear, actually, if we kept increasing the density, we could keep going up this slope. It does drop off eventually, but but we can keep going up and up that sensitivity. So there's a genuine question to say, okay, how far can we go up there? At what point can we maybe, so where would an invasive recording, like a microelectrode recording be? You know, that's going to be somewhere up here, isn't it? But can we ever get there, or can we get close? Which I think would be quite exciting. I'll whiz through the next bit because we're running out of time.
We have until 12. So.
Okay. So one of the problems is when you want to enable free movement, if you've got any background field in your shielded room, which most shielded rooms do have a little bit of background field, then as you move a sensor relative to that background field, it will see a change in magnetic field. So as you move your head, you'll get these big oscillations in magnetic field. What does that mean? Well, most people move around a little bit during the scan, even if it's just the sort of imperceptible head bob. You know, if you sit there and watch somebody, their head bobs with their heartbeat. So even if it's really, really imperceptible movements like that, you've still got these small movements. Obviously, children move a lot more. So you get these, and most of that movement is low frequency. So if you actually look at the spectrum of data, you get these big increases in low frequency interference. So how do you get rid of that? What can you do about that? Well, the answer is simple. If it's caused by the background magnetic field, so you make the background magnetic field zero, or at least as small as possible. And again, you've got this capability in your new lab. So there's coils built into the walls of the room, and you switch those coils on in a clever way. You can measure the background magnetic field and you can drop it down to zero. And so that's what we did here. So this we were looking for. In the red line, you should see a 6 Hertz response, and it's sort of there. So the black line here is rest. The red line is the active window, and you should see a little spike at 6 Hertz, and you can kind of see it, but it's sort of buried in all this noise. Then if you drop that background magnetic field to zero, then all of a sudden both of these things come down here, and that's what happens. You get a nice 6 Hertz response. So this controlling the background field is really important to be able to enable free movements. So we have different coil systems to do this. I won't go into detail. This is a coil system that allows that field null, to allow that controlled region of field to move all around the lab. And so this is one of my colleagues, Niall. He doesn't move that fast in reality, but he's sort of walking around the lab whilst we're doing a MEG experiment. So that field null is sort of following his head around. So if he kneels down in a minute or something. And so that allows there we go, allows the field null to follow him in real time. And then we were able to get nice brain imaging data. I think one of the problems with that allowing people to move around the lab is that you then have, in our case, 64 massive cables dropping off their back. And so the system looks like this, all these massive cables. So working with the Q-spin guys, again, this is a paper written by Holly. The Q-spin guys had this sort of, if you like, vision of a helmet with just a backpack, all the electronics in the backpack, and then just one little wire. So that was the 2022 vision. That was the 2024-ish reality. So we built that system. You can see that we really weren't very good at building TVs, but we did get there with the backpack, and it really does work. And this is now recent data that we've got. So we were really worried about, especially about attaching all these massive cables to patients. But we've just with this system, so you can see there's actually 2 wires that come out the back. We've just completed a study with 20 patients with multiple sclerosis who find it difficult to move. And we wanted to scan them sitting down and scan them standing up. And that's what we did. This is desynchronization and beta rebound from patients as they move their fingers. These are the patients sitting down. These are the patients standing up. You can see sort of similar differences, but actually the differences between patients and controls are less marked when they're standing up for some reason, but you don't understand. But I guess I'm showing you it to just prove that we can do sort of sitting down and standing up experiments. We've got, again, very early days. This is data hot off the press, but it does seem these are measurements of functional connectivity. It seems that functional connectivity changes fundamentally when you measure it when a person stood up compared to when you measure it when a person's sitting down. And obviously we always do scanning sitting down. So actually, if you're standing up, moving around, how is that changing our brains? And it looks like something quite fundamental. It's work by Ben Sanders. And then, of course, if you start trying to go from sitting down to standing up, this is something that the Parkinson's disease guys are really interested in. So apparently the get up and go task, can you stand up and walk, is something that people use in Parkinson's disease clinically all the time. So we've got data going from sitting to standing and back to sitting. And what happens when you have things like freezing of movement, freezing of gait in Parkinson's disease. So all of a sudden, you're not now lying in a scanner. You can measure brain activity while people are trying to do these tests. So I'll finish with just a few minutes on imaging children. So I said from the start that one of the big advantages of OPMs is that we can get them closer to the head. People can move around, and that's ideal for imaging kids. So we've just completed a study. This is work in collaboration with Margot Taylor's group in Sick Kids Hospital in Toronto. So in this initial study, we did 27 kids, 26 adults. Our youngest children in this study were 2. The eldest were 13, so quite a wide range for no better reason than that's who we could get. And it was, again, it was a sensory task. So we were stimulating either the index finger or the little finger. So first, some data in a single child. So this is the localization for the index finger. It's a localization for the little finger. So it follows what you might expect it to do. Which is nice. We get nice beta desynchronization and rebounds. This is what we get if we look at the different age groups. So 2 to 6 year olds, 7 to 10 year olds, 10 to 13, and then the adults. And again, you can see these beta effects slowly build up over time to the sort of classic adult response. And if you plot that on an individual subject basis, you can see sort of quite nice changes. There's nothing new there. We knew that that was going to happen, but we did the study to sort of validate the technology. So can we see an effect that we know that we should expect? So people had done this sort of thing before using EEG, but obviously they hadn't got the spatial resolution to be able to map it. People had done it as well in MEG, but in older kids, so probably 8, 9 year olds upwards, where we were able to do it from age 2. So I think that was an important validation that this is now, again, hot off the press data. It will be presented at BioMag for anybody who's coming, work by Natalie Rhodes, led by Sick Kids. But this is now measuring gamma band oscillations in children, again, going down to 2 years old. This is now a study that pulls data from Nottingham and from Sick Kids using 2 identical systems, so they're the Circa systems. So we were able to pull the data across the 2 systems to get 102 volunteers. The first thing is, if we look at all the different age ranges that we studied, so 2 to 4, 5 to 8, 9 to 13, et cetera, all the way to the adults, and we look at where these gamma bands are occurring in the brain, there's no difference. They always come from the visual. But actually, if we start looking now at what those gamma band oscillations look like, they seem to look very different. So this is what they look like in adults, with a big response about 60 hertz. In children, it's much, much lower, and it seems to split into these 2 different bands when you get to about age 8 or 9. before turning into the sort of classic adult response that we all know. Now, that would be really difficult to measure in EEG and probably quite difficult in conventional MEG, because you couldn't go that young and the kids would probably move around and get very bored because it's not a very interesting study. But we could measure it. And again, this is very new, but this is if we apply a DCM, so a sort of canonical microcircuit model of what's going on. This is work by Krish Singh. So Krish developed this model. So don't ask me too many questions about it, because I don't know how it works. But you basically fit the gamma band data and you try to understand what's going on. Again, this is work led by Natalie at Sick Kids, and we can get quite nice differentiation between inhibitory and excitatory processes going on in this microcircuit, and the inhibition seems to go up, and the excitation goes down with age. So I'll stop talking, but just to say, I think OPMs are probably going to replace SQUIDs as the sort of fundamental building block of MEG systems in the future. I think most people are convinced by that. But the question really to me is not what can they do what SQUIDs do, but can they do what SQUIDs can't. And so for you guys who are getting one of these systems, what are you going to do with it? What are you going to be able to do with it that you haven't been able to do before? What problems is it going to solve? And so hopefully, between the data that I've shown in children going to very, very young kids, and the group in Brussels have gone even younger, they've gone down to babies in the first few weeks of life. So that's one area where you can go with OPMs that SQUIDs really can't go. I think we can get better sensitivity in the ways that I've shown by going to very high density. So even with the slightly higher noise floor, we can still surpass the sensitivity of SQUID systems, and that has to be an advantage. We can start to scan patients, so maybe elderly patients while they're standing, sitting, walking around, so we can actually engage the brain circuits that we know are failing in these people with things like with problems like Parkinson's disease and things like that. So there's lots of reasons to be excited, I think, about your new system. Lots of things that you can think about doing, but you have to sort of get away from these ideas of conventional MEG system or conventional neuroimaging. You might lie somebody in an MRI and to start to think about new ways to scan people. I will stop there, except to say none of this was done by me. It was all done by lots and lots of other people. So thank you to everybody who's contributed. Thank you to all of our funders, and thank you for listening.
That was excellent. Thank you so much. That's really wonderful overview of OPMs and the work that you guys have been doing. It has been so inspiring to us. So yeah,